Welcome once again. And in this lesson, we are going to talk about the fully associative mapping in cache memory. Right, so we are going to talk about the concepts of fully associative mapping. We are going to look at how the fully associative mapping works. We're going to look at an example, and then we'll talk about the advantages and disadvantages of the fully associative mapping in cache memory. Right, so without wasting much time, let's get right to it. Okay, so what is fully associative mapping? So fully associative mapping is a cache memory technique where any block of main memory can be stored in any cache line. Unlike the direct mapping, which restricts each memory block to a specific cache location, fully associative mapping allows total flexibility. So it treats the entire cache as a single pool of lines, and a block can go anywhere depending on what's available and managed by the cache controller. Now, because it offers maximum flexibility, it reduces the conflict messes that we talked about in the cache memory. All right. Now, how does the fully associative mapping work? So this is how it works step by step. So first, the main memory is divided into fixed size blocks, right? Then the cache is also divided into lines, right, with each line holding one memory block. Now there is no fixed mapping like the direct mapping, so any memory block can actually be placed in any cache line. So the memory address is only split into two parts, which is the tag part or the tag bit, which identifies the memory block, and then the offset bit or the offset part, which specifies the byte within that block. That's all. There is no index because the blocks are not restricted to specific sets or lines. Now let's break down the memory address. So we said the memory address is equal to the tag plus the offset, right? So the offset selects the byte within the block, the tag identifies the memory block, and as we said, we don't have any index field in the address. Right, so let's look at the data access process. So when the CPU requests data, this is what happens. It extracts the tag and offset from the address, right? So the tag is compared with the tags of all cache lines to check if the block is already in the cache. Now if there's a match, it's a cache hit and the data is retrieved using the offset. Now if it is not this one, if it is not a match, then we call it a cache miss, and the data is fetched from the main memory and loaded into the cache line. And one of the existing blocks may be evicted based on the replacement policies we talked about, like the least recently used policy. Alright, so let's break down the address structure in fully associative mapping using this example. So assume a cache size of 4 kilobytes, a block size of 32 bytes. So in order to get a cache lines, we simply divide the cache size by the block size to get 128 cache lines. And then consider a main memory size of 64 kilobytes, which gives us what 2048 memory blocks. So since the address is 16 bits long, given from the main memory address, 2048, which is 2 to the power 16, since the address is 16 bits long, the fields are as follows. So the offset will be remember the block size is the offset, so it's just simply 2 to the power 5, and we take the 5 as the offset bit, so 5 bits, and we use that 5 bit to pick a byte within the block, right? Then we simply subtract it from the main memory bit, that's the 16. So 16 minus 5 giving us 11 bits, and we use all the 11 bits for our tag. So use it to uniquely identify the block. So our tag bit starts from bit 15 to 5, which is the 11 bit, and our offset bit starts from bit 4 to 0, which is our 5 bit. Alright, so what are some advantages of the fully associative mapping? Okay, so this method actually have several strengths, right? And the first one is the flexibility. which means that any block can go into any line, right? Which drastically reduces conflict and then thrashing as compared to the direct mapping. Also, this technique actually has a higher hit rate because of the flexible placement. It can take better advantage of locality in programs, and also it is ideal for small caches, right? In that it works especially well when there are relatively few lines to search. All right. Now, however, there are some trade-offs. Okay, so the first trade-off is in terms of its complexity. So since the system must search all the cache lines for every access, it needs extra comparison logic. Also, there is higher power consumption in that all line comparisons consume more power than the single lookup used in the direct mapping. And then finally, the scalability issues. So as the cache grows, the cost and delay of searching increase significantly, which is why this is rarely used for large caches. All right, let's walk through an example, right? Let's walk through an example, right? So memory, let's take a memory size of 64 kilobytes, which is 2 to the power 16 bytes, a cache size of 4 kilobytes, and a block size of 32 bytes. So the cache lines will give us 128 lines. The memory blocks will give us 2048 blocks, right? So that gives us our offset bit to be 5 bits and our tag bit to be what, 11 bits, right? So for a memory address like 0x1234, we can extract that the tag bit will be from bit 15 to bit 5, right? And then the offset bit will be from bit 4 to 0, right? So that's if the address is 001 0010 0011 0100, right? Which means that the tag is bit 15 to 5. So we just take the 0001 0001 right? And then our offset to be 10100. All right. Now suppose we later access 0x2234 in direct mapping. Both addresses would conflict, but in fully associative mapping, they can both reside in the cache simultaneously, eliminating the conflict. Right. So in conclusion, we can see that fully associative mapping gives us maximum placement flexibility, right? It avoids the conflict problems seen in direct mapping and often results in a higher hit rate. However, this comes at the cost of hardware complexity, power, and speed, especially as the cache size increases. So, I mean, it is most effective in smaller caches where flexibility is critical, but becomes less practical in larger systems without expensive hardware. Right, so this brings us to the end of our lesson on fully associative mapping. Right? I hope by now we have a fair idea of what fully associative mapping is. Thank you.